Yeah, thank you very much for being here. Let's get started with a quick survey. Is anyone here worked with Reactive Streams? There you go, a few hands. Anyone use them in anger in production? Yeah, a few of them. This is good. My main point is, regardless of the tooling you use, whatever implementation you're after, streaming apps are becoming more and more part of our lives as back-end developers, as basically the need grows to process more and more data, right, as soon as it's come. Now, and just like any other apps, streaming apps need to be monitored, right? So this talk is going to try to analyze the challenges of monitoring a reactive stream application, and we'll try to answer some questions around these challenges, and we'll see some practical examples around Akka Streams, but most considerations are applicable to any sort of streaming app or framework. Now, very quickly, I'm assuming you're all familiar, or I'm actually hoping that you're all familiar with the advantages of monitoring your application in the first place. So monitoring is about collecting and tracking what's going on in your system. The reason being, we want to be the first to know if something goes wrong, right? Or if something goes particularly well, but being inherently paranoid, we want to be the first to know if something goes wrong, right? Now, for this reason, it's particularly important to instrument your app or your system with monitoring from the very start of the development process, and not just treating monitoring as like a nice cherry on top where everything is like in gold plating phase. And of course, monitoring is generally enabled by metrics, and these are raw measurements of behavior that you can collect. And of course, you can think about countless types of metrics. You can have your very own business metrics that you can collect. You can talk about metrics in the CI/CD context. You can have low-level system metrics, as in memory, CPU, whatever. But when it comes to reactive streaming, essentially there's two key metrics that are very important to understand how your whole app is faring. And we're going to talk about these two today. One is basically want to know how many operations or requests or data items, how you name it, are going through your stream. And this is what we call throughput usually. And then we want to know, crucially, where its bottlenecks are. And this basically means, in the reactive stream context, if and where your stream is back pressuring. So you can think of many more metrics again that you might collect, and you should, in your stream. But these two particular alone will give you a pretty good understanding of how your stream is performing. And we're going to see why these two are important and what specific challenges they pose in the reactive streaming context. So we'll start with throughput here. Why do we need to measure throughput? If you think of your traditional web service, you usually think of throughput as in terms of requests per unit of time. So we usually have some SLA, right? We want to abide, and we probably want to be able to sustain a certain throughput going through your app. So this is pretty classic. This is true also for streaming apps, of course. However, when we're dealing with streaming apps, some of the assumptions that we make for traditional web services are not there anymore. We have two kind of non-linearities of sort that we need to deal with. And these are two challenges for us. First of all, concerns topology. This is your this is your traditional web service. You have a linear topology, you have requests in input and responses in output, right? However, in a more kind of generic streaming app, you have potentially a much more complex topology where you have a variety of publisher, subscriber, fan in, fan outs, any sort of graph, right? So this is the first thing to keep in mind. Secondly, in a traditional web service, you present one request in input and you expect one response in output, right? If the service is healthy. Now, if you're dealing with a more generic streaming app, you don't necessarily have this linear correlation between inputs and outputs, right? The generic streaming processor or flow materialization, if you live in the Akka Streams world, is not a function. So in a function, you have one input, you expect one output. Here, for one input, you can have from 0 to infinite outputs on the other side, or the processor might even start producing outputs if no inputs is given to them. So you can imagine streaming applications as basically a generified version of your traditional web service And this is actually how a web service is modeled in things like Akka HTTP. If you're familiar with it, Akka HTTP sits on top of Akka Streams, and it's actually modeling web services as a flow of incoming requests and outgoing responses. Now, this said, does it make sense to monitor like throughput for a whole streaming app? Not really, right? Throughput is something you want to monitor in specific points in your graph, right, in your topology. So one way to solve this is basically to instrument your graph with multiple checkpoints in the form of transparent processors. So these are basically sections of your graph or of your pipeline sorry, where the input is basically transparently presented to the output and metrics are collected for you. Now, the main idea is to have basically reusable components that you can plug wherever you want in your graph to get a pulse on your streaming app, how you're doing. Now, you might not need to put these little checkpoints in all of the junctions in your graph. It's actually good to give the developer the liberty to kind of place these in like whatever sections are more relevant. So let's see how this translates into some code. So we're going to use Akka Streams. So let's see, we have a source that emits a random integer. This is what we have on the top. Random integer every 10 milliseconds, right? We have a filter that throws away odd numbers. And then we have a sink that prints, right? So this is a very simple Akka Streams pipeline. Even if you're not fully familiar with Akka Streams, it's pretty readable what it does, right? So, and it's a very simple example. It's already an example where you can see you will have different throughputs in different points of your pipeline, right? Because you have a filter element. Now, source, flow, and sink, if you're not fully familiar with Akka Streams, again, they can be concatenated with a very fluent DSL using via and run with to start the flow of data. So to go to the throughput measurement part, we can now create a simple checkpoint flow to measure the throughput. This is pretty simple. It's going to be a transparent flow that creates a metric. Now, here we use come-on, for example, as a backend, but you don't have to stick to that. And essentially, you give it a name to mangle it in the come-on backend, and this basically increments the counter every time something passes through the stream. So this is pretty trivial, right? We can now place these transparent flows wherever we want in our pipeline and give them meaningful names so that we can track them in whatever backend monitoring system you have. The key thought is that these are basically completely generic and will work by being plugged in whatever Akka Streams graph you have, right? And this is, of course, courtesy also of Akka Streams graph stage composability. So this is what you would plot on a throughput dashboard for this very trivial example, right? So the unit here is elements a second. So you can see we're producing around 100 elements a second. So this is 1 every 10 milli. This is the rate we're generating stuff at. And basically, after we process, that's the filter, we're left with about 50 elements a second, right? Because we dropped the odd one. So this is pretty simple. Sometimes it's even practical to aggregate these two metrics or two metrics in two different points of your graph to get some sort of relative throughput of kind. Now, this would be basically a ratio between throughput collected at two different points, right? So this can give you an idea of how many, like the ratio of how many events are being dropped or conflated maybe if you're having a ratio lower than 100%, or maybe how many you're generating or expanding if you have a ratio higher than 100%. Now, in this case, you would have a relative throughput of 50%, of course. Now, so throughput is what we've seen, and it's kind of the simpler of the two to monitor. So let's move on to something slightly trickier. Let's move on to back pressure. Now, why do we need to measure back pressure at all? And this is the key question. So we can explain this with an example to make this a bit more concrete. So we have a streaming app that you see here. You're consuming from Kafka. You have some processing logic. You mark some elements as invalid. You want to log them, send them to a log file. You mark some of them as valid. You want to put them through, store them somewhere using some HTTP API, and then at the end commit the Kafka offset. So this is a pretty common pattern, right, when consuming from Kafka in general and when writing data pipelines. Now, let's assume that we are actually instrumenting the graph for throughput measurements using the thing that we just coded together, right? And let's assume that we get back the following results. We are consuming from Kafka at 100 a second. We just mark roughly a quarter of them as invalid, put forward 3/4 of them, and then these are going through, being stored and committed, right? So we're all happy that we have our measurement here, but we have two possibilities now. Either we're happy with these numbers, and we can all go home or watch more talks, or we're not, right? And this means that they're not matching our SLAs. And let's say, for example, that this is the case. Let's assume this Kafka topic produces thousands of messages, and this guy alone cannot cope, right? Lag would spike through the roof, and we'll all be very, very unhappy. Now, you can solve this in a few ways. One might think, okay, we can deploy a bunch of these. It might not be enough if you don't have enough Kafka partitions. Maybe your boss will not be very happy with your AWS bill at the end of the day. So, you know, that might not cover it, right? So we need to understand where the bottleneck is in this guy in order to optimize it, right? If we can at all optimize it. But we need to understand where it is first. And you can see that the throughput readings here are pretty useless to us. We cannot really understand where it is. One might assume it's the API, maybe. But it could be the commit stage if we're committing too frequently to Kafka. We're not really sure. And this is because all the readings, they align to the slowest pipeline stage. And this is because of back pressure. Back pressure is actually a very desirable behavior of reactive streams. And it makes sure that we never overflow our systems by consuming more messages than the one we can actually process, right? And basically, this makes our systems resilient by design. So it's very desirable when we're dealing with unbound stream of data with unpredictable volumes. And this makes important to understand how reactive stream works. So let's spend like 20 seconds just recapping this. Essentially, in reactive streams, it's the subscriber itself that requests more element, right? Request for element is basically propagated upstream up until someone who can produce elements, in this case a publisher, emits this amount of elements. And these are in turn propagated conversely downstream to the subscriber itself. So essentially our pipeline is back pressuring in a specific point, so say between this processor and this subscriber, when it's waiting for a request coming from downstream. Right? This means that the subscriber or sync materialization is busy and cannot process new elements, so it stops requesting, right? Conversely, when a request has been made and we're waiting for an emit of something from upstream, this is a state when our pipeline is not back pressuring, right? So how can we measure this? What if we could somehow measure the time spent between waiting for a request from downstream and the time spent waiting for an emit from upstream? A ratio of these two would give us basically the relative amount of back pressuring that goes on in one specific point in your pipeline. And basically in this sample timeline that you see here, you might mark with green the portion where the pipeline is not back pressuring, and with red the portions where the pipeline is back pressuring. Now, this is easier said than done, because in reactive streams, in general, asynchrony is prescribed, right? This means that requests and emit might happen in very different contexts, so it might not be an easy problem to solve, right? Thankfully, in Akka Streams, actually Akka Streams makes our lives easier here, basically by sequentializing some of these events in the same context. So next, we'll see how we can get this done in Akka Streams itself. So enter the GRAPHSTAGE API. This is basically Akka Streams' lowest level API. It's an API that basically makes you define any streaming stage. So bear in mind that any stage that you use in Akka Streams uses this underneath. And basically lets you define a bunch of ports for your stage, and it lets you attach handlers for these ports. It lets you define on-pull handler for output ports and on-push handler for input ports. Now, just as an example, this is how map is done in Akka Streams under the hood. So basically, you have two ports, in and out. They're typed, right? and then you have a logic with two handlers, right? So when upstream pushes, basically it grabs the element from the port, applies the function that you create the map with, and then pushes the transformed item downstream. When downstream pulls, conversely, it just propagates the pull upstream, saying whatever is upstream, please give me more because I'll be able to transform this and send it over, right? So this is the API that Akka Streams gives us. We can leverage this to measure our back pressure. So the most important thing to keep in mind that is the graph stage in Akka Streams is never accessed concurrently, basically. It's just like the inside of an actor. So this means that the order in which these handlers are called is deterministic. We can basically rely on these to be called in the strict on-push, on-pull dance, right? And this makes it a lot easier for us to measure back pressure, and we'll see how. Basically, it makes it possible to discern the time between requests and emits, or on-pull, on-push calls. So let's create a graph stage that does that. So this is a very simple implementation of this. We can keep two timestamp variables. One is last push and one is last pulled. We can use vars again inside the stage. This is basically like the inside of an actor. It's one of the few places in which you can do this with impunity because the Akka Streams infrastructure makes it possible for you to do it safely. Now, we can create a histogram. Again, we use common here. We store the back pressure readings in it. You can use whatever is your favorite backend. So when a pull comes in, basically we first propagate the pull upstream, and this is just what map does, and we've seen this. And then we can mark this last pull timestamp as of now, right? Now when a push comes in, we can actually do this calculation now of the ratio between the time spent waiting for the pull and the time spent waiting for the push. Like this is quite simple calculation. In this case, it will be a percentage, and 0% will mean pipeline is never back pressuring in this place, and 100% means it will always be back pressuring. I mean, it's always back pressured in this place. But more likely will be something between the two, right? Now, this stage can be used in the same way that we use the throughput meter here. We just place it wherever we want in the graph, and we get a pulse, right? So let's consider the same example that we've seen before. So we had a source that produced a number every 10 milli, right? And then we had a simple filter and a print, right? So say we instrument the stream to monitor back pressure as well. What do you reckon we get as back pressure reading? Give you just a second to think. This was a tricky question. You get 0 back pressure here. So essentially, because the stream is very fast, we filter and print, it's everything we do in the stream is much faster than the 10 milliseconds at which we emit the numbers, right? So this means that both checkpoints will never back pressure, right? It tells us that the pipeline basically has no bottleneck, or actually better, the pipeline's bottleneck is the source itself, right? Now, we can spice this up a little bit by replacing the filter logic with something much slower. We can use the facility from akka.pattern, which is called after, to simulate like 250 milliseconds operation here. And we can use map async to run futures inside Akka Streams. As you probably know if you're familiar with the API, this is basically something that runs futures inside your stream. And the crucial bit here is that if the maximum parallelism that you give to map async is reached, then the stage starts back pressuring, right? And in this case, max parallelism is set to 1. So basically, this stage will run futures of 250 milliseconds sequentially, one after the other, right? Note that we still keep the filter around. So let's see how the dashboards change, both of them. So if we start with the throughput one for a second, we see that the graph is pretty similar to the one that we were seeing before. We just noticed that basically the throughputs decreased considerably, right? Of course, because we're doing extra work. So now we produce roughly 4 elements a second, because we basically have 250 milliseconds delay. And we still have around 50%, right? Because only the even one makes it through the processing stage. So this doesn't really tell us where the bottleneck is again, right? So we could have put the slowdown in whatever part of the pipeline, and we would still have got this graph here, right? So let's check the back pressure graph for a more interesting insight. This is what we would plot. Now we can clearly see that the produced checkpoint is now back pressuring, right? Almost 100%. Why? This is because it's got a very slow downstream that starves it of requests, right? So at the same time, the processed checkpoint is never back pressuring, that's the yellow line, because it's got plenty of requests from downstream. And this is because the sink that prints is always hungry for more because it's very quick at doing its job, right? So this tells us that the bottleneck is actually the processing flow, which we know already because we put the 250 milli there, but that's not really the point, right? So basically, a more subtle but still interesting point is that the green line is not 100%, right? If you check it, it's around 96, 97%. This is because the source is still emitting at a rate of 10 milli, right? So for this 10 milli, for the fraction of this time, the checkpoint is waiting for the source to emit. And this is a fraction of its time in which it's not back pressuring, right? And this amounts roughly to 4% of its time. That is basically 10 milli over 250 milli. Now, this is nice because we know where the bottleneck is, but it's only half the job, right? What can we do to ease things up when we find a bottleneck? Well, this is a whole different discussion, right? It very much depends on the kind of workload that you're performing and a few other things. But basically, Akka Streams gives you a variety of tools and weapons that you can throw at your stream to shape basically its throughput. And you can basically increase parallelism, which is one thing that comes to mind first. You can add the synchronous boundaries. You can use map async unordered if you don't care about the order. You can add buffers. You can use maybe conflation if you can afford to be lossy in your stream. There's a whole things you can do. I won't go in more details here because this could be an entire talk by itself. But basically, for the top class blog post, be sure to check out this from Colin Breck's blog. This is really worth reading for anyone who uses Akka Streams. It's basically a very, very concise summa of basically multiple tips to make your Akka Streams very performant. So summing up, we've discussed an approach to monitor Akka Streams applications, but some considerations that we made can be applied to basically all reactive streaming implementation out there. The key thought is that you need to make sure that you monitor your streaming apps in different points of your graph. And crucially, you need to get a good understanding of how both data and back pressure propagate. So reactive streams are bidirectional streams. So there's data going one direction and the requests go in the other one. You have to make sure that you understand both of them, because otherwise, if you only monitor the data or the throughput, or if you don't monitor at all, God forbid, you will end up with a very opaque stream that is very, very difficult to reason about. And this basically means that as soon as you have a problem, you don't necessarily know where to put your hands, right? Now, this stuff that I showed you, I put it on GitHub as a micro library. So again, feel free to check it out. If you use Akka Streams, I'll be very interested in hearing some feedback. Essentially, this gives you a single checkpoint stage that gathers the metrics that I've just told you about. It does more. It gathers push-pull latencies. It also gives you metric that help you diagnose liveness issues. This is something that I didn't explain today because there was not enough time. But what I showed you today does not necessarily help you in case you've got liveness issues in your stream. So there's something to help you in that direction as well. And it counts failures and completion if this is something that that happen often in your pipeline. Now, there is a microsite as well for documentation, so feel free to check it out. It's currently available for Common and Drop Wizard backends, and it's available on Maven Central. So really, yeah, if you want to take a look and give some feedback, I'll really appreciate it. So this is all for me. I really thank you very much for your time. If you want to get in touch, these are my handle. Feel free to grab me at the conference. I'll be around for these 3 days. Thank you very much for your time.